I'll speak about fast radio bursts. Now we know that these sources are examples of neutron star activity, and this activity is related to plasma emission with extreme properties. And what is more important, the mechanism of this emission is still unknown, so there are lots of things to do. And actually every day, nearly every day, new results appear, and while listening to very interesting talks in the morning session, I was checking today's archive, and I found out that a very important major discovery was presented today. For the very first time, radio astronomers detected emission from repeating source of fast radio bursts at very low frequency, nearly at 100 megahertz. So I'll start with brief, as I don't have much time, introduction, reminding you general properties of fast radio bursts, and then I'll present some important results obtained this year in the field. So there are lots of types of radio transients in the sky, and fast radio bursts, you see them here on the top left. They are really extreme. In this diagram, they are well separated from other types of radio transients. And the whole story started in 2007, when Dan Plormer and his collaborators reported the first event. At that time, the origin was absolutely unclear, and even many people believed that this is something artificial or happening in the Earth magnetosphere and so on, so it was not clear that it was an astrophysical phenomenon. But since 2013, since the paper by Thornton, and the picture on the right represents a plot from their paper, from 2013, we are sure that this is an astrophysical phenomenon. So fast radio bursts are very brief, millisecond long radio bursts, initially detected at frequencies about 1 gigahertz. And the estimated luminosity is about 10 to 40 ergs per second in radio. So this is something really extreme, because we know short, powerful radio bursts in astronomy, but 10 to 40 ergs per second, this is something which was not seen before. At the moment, in the Catalogue, slightly more than 100 events are reported. We are sure that there are lots of, at least tens of unreported events, which are still analyzed. And also there are several repeating sources, and there are thousands of repeated events. And for such repeaters, there are separate catalogs. And as you see, there are telescopes all over the world, in the northern and in the southern hemispheres, which detect these sources. They are very numerous, so their rate in the universe is very large. And that's why some hypotheses were rejected based on this rate. Considering very bright sources with flux above 1 Jansky, there are many hundreds of events per day in the sky, and if we go down to sensitivity limit of present-day telescopes, there are thousands of events in the sky. Of course, due to very small field of view of radio telescopes, it's difficult to detect many of these sources. About the field of view. Initially, localization of fast radio bursts was very poor, and people just could say that the source appeared in the field of view in one beam of a radio telescope. So localization was slightly better than the size of the moon in the sky. Of course, it's impossible in this case to say something about the exact position of the source. The situation changed when the first repeating source of fast radio bursts was detected. This source repeats very frequently, so it was possible to use several telescopes situated in different continents to observe such sources and then to determine position precisely. This allowed to identify the host galaxy of this burst, and it was a direct proof that they are extragalactic sources. In this particular case, the distance is 1 gigaparsec. And so the luminosity estimate I told you before was also confirmed. So it became clear that we are dealing with a very powerful phenomenon, most probably related to neutron stars. I'll speak about hypothesis a little bit later. And of course, it was necessary to to describe the emission mechanism, what is happening in plasma around neutron stars, which finally produces so strong radio bursts. Now we have many localization, well, many means 10 well-localized sources. What is more important that now not only repeating sources are well-localized, and I would say among these 10 sources, the majority is non-repeating sources. This is happening because of new instruments, new systems of radio telescopes start to operate. And in this case, this is particular system ASCAP, the Australian Square Kilometre Array Pathfinder. So the second repeater was reported by another very important instrument, CHIME, in Canada. Then CHIME reported about a dozen repeating sources, and now altogether there are about 20 repeating sources. However, most of them repeated just twice maybe, and there are very few sources with many pulses. But these sources with many pulses, they show particular feature. They show periodicity. At first, periodicity was detected for this source, and actually today's paper in the archive about low frequency detection is also about this source. So in this case, roughly 16 days periodicity was detected, and in the case of the most prolific repeater, the periodicity is longer, more than 100 days. The origin of periodicity is still uncertain. It can be a binary system, or it can be maybe a precession of a neutron star. These are two main approaches. To probe plasma, we need to measure polarization, and this is successfully done in many cases. At the moment, in the catalog, you can find data about polarization for roughly 20 sources, which is a significant fraction, and these can allow to understand better properties of plasma, and I'll come later to one important discovery of this year related to polarization. Okay, so since 2007, people started to propose different models to explain fast radio bursts, especially since 2013, after the paper by Thornton and co-authors appeared. People started very actively to propose different ideas. Roughly, they can be divided into two main groups, neutron stars and exotics. Neutron stars, because of course they are candidates number one. We know that neutron stars can emit very short and very intense radio bursts. And exotics, because people like exotics. Many theoreticians have their favorite paper, favorite theory and papers about cosmic strings, white holes, and axions. And all these models were applied to explain fast radio bursts. However, as data was growing, early ideas were rejected one by one. Exotics was closed based on repeating sources, extreme rate of these events, and so on. Catastrophic events also are excluded, at least if we want to explain all FRBs in one model, because there are online detections and there are very rapid follow-ups in other wavelengths. Thus, we see that FRBs are not related to supernova, gamma ray bursts, neutron star coalescence, and so on. Compact objects plus something like falling asteroids on neutron star and so on are also excluded as the main explanation, I would say. And up to this year, we were left with two main ideas. Either they're magnetars or they are extreme pulsars. The main difference is either we emit the energy of the magnetic field or sources are rotation powered. So now I'll come to say the main part of my talk, to results of this year. The magnetar model was proposed already in 2007, so in this paper actually in October 2007, and the main prediction was that there are galactic magnetars. They might show flares too, maybe very seldom, but still they might. And since there were no detections of bursts from galactic magnetars, there were some doubts in the magnetar model. In this year, the situation finally changed. So now we know, and I'll show you results, that actually magnetars at least can be sources of FRBs. We see FRBs from magnetars, and the main question now is not what is the source of FRBs, but where emission is formed, either deep in the magnetosphere or in the outer shock waves. So even before this year, well, last year, people started to see very short millisecond duration bursts from galactic magnetars. So the first example was related to this source, XT 1810. You see the burst by itself on the right. You see that this is a millisecond burst. However, it's very weak. And their properties are significantly different from FRBs actually, but still we see that magnetars can produce millisecond radio bursts, and now we detect them in many numbers. This is another paper, already paper from this year, and you see on the top panel many millisecond bursts detected at high frequency. They appear nearly every rotation period of this magnetar, so they are correlated with X-ray light curve, and it tells us that continuously in this magnetar at least something is happening, something interesting presumably, which results in this phenomenon. Another paper which appeared just a month ago represents old observations, and I don't know why people didn't reduce this data before, old observations from 2009, during which they observed one magnetar jointly in X-rays. So you see names of three space experiments, Chandra Swift and Kronos Wind, and with a radio telescope, 64-meter telescope at Parkes in radio. And the red line represents radio light curve. We see bursts, and also we see an X-ray burst, not coincident with a radio burst. So this is also a new phenomenon. Such behavior was not observed before, but now we also have this puzzle. Still, they are not the major puzzles and not the major discovery of the year. The major discovery is related to this soft gamma repeater. And I really think that in the list, at the end of the year, people like to make lists of top discoveries in different fields. I think in astronomy, this is #1 this year. So this discovery is related to this galactic magnetar. It's situated not very nearby. Actually, distance is not very certain. So it's about a factor of 50%. So let it be 10 kiloparsec. This magnetar was discovered just recently, 6 years ago. It showed intense high-energy flares. It was reported, for example, in this paper. And this April, the source was activated. And people started to monitor the source. And what is more important now, thanks to CHIME, thanks to other instruments, we can monitor radio sky nearly continuously. Not the whole sky, actually, but very large areas. And luckily, finally, people detected simultaneous intense millisecond radio burst from a magnetar simultaneously with intense and peculiar, and as I'll show you later, high-energy burst. So in radio, the main instrument was CHIME, another was STER2. I'll also show the results. And in high energy range, it was Kronos Wind. Chinese satellite, HMHD, XT might be its misprint, Integral and Agile. So these are results from China. We see a double burst, millisecond duration, 30 milliseconds between flares. And another radio instrument which detected the source is a very simple installation called STARE-2. There are several stations in the United States. They're not very sensitive, but they are looking for bright bursts, and they also identified this burst. They couldn't show that that there are two separate flares with 30 millisecond gap. But still, they obtained very good measurements of the flux of this source, and it is really a very intense event. And it was coincident on the sky with the magnetar. What's important that the flare in radio was coincident with the flare in the high energy band. And here I show results by Konos Wind. The paper, of course, everything was published on the archive, and that's why I'm referring to the archive. But the paper is will be published in January in Nature Astronomy. So you see the X-ray light curve, and with blue, positions of the radio burst is shown. So this flare in X-rays in gamma was really extreme. In this plot, again, this is a Konos Wind data. What is shown, peak flux of different bursts and peak energy on the vertical axis. And the red corresponds to the flare happened in April, which is coincident with a radio flare. And we see that this is really a peculiar flare. So something peculiar is happening in the plasma around this magnetar. There are also data from other satellites. I have to skip it, I guess. The source was monitored later in radio and X-rays, and people detected more weak millisecond radio bursts. Scaling shows that we are unable to detect high energy flares if ratio of X-ray luminosity to radio luminosity is the same for all bursts. Still, it's important that the source can be monitored, it's bursting, it's active, and more data appears. Another discovery of this year related to plasma around magnetars was published in Nature Astronomy in November. Or in Nature, I don't remember, maybe in Nature. These are results from the FAST telescope, and they observed one of repeating sources, and they measured polarization. They showed that polarization angle is rapidly changing from burst to burst. And this tells us probably where bursts are generated. Because if it happens in the outer shock wave, then the magnetic field must be very regular there. And we don't expect rapid changes in polarization. But if everything is happening deep in the magnetosphere, even small spatial shifts of the emission region will produce significant changes in polarization. So maybe now we are closer to the answer. We know that magnetars are producing fast radio bursts, and even we strongly suspect that the emission is emitted deep in the magnetosphere, not in the outer shock waves. So I will not maybe read all these current grading of hypotheses. I'll very briefly say a few words about future observation in the last minute of my talk. So now there are many telescopes observing. Some of them are relatively old, like Parkes. Some are new as FAST and at most. New installations appears, and I already told you about ASCAP. The paper in the morning is mostly related to LAFAR and Apertif observations. Apertif is a new, say, set of instruments on the Westerbork telescope in Netherlands. In future, of course, we'll have SK, but we have to wait for a long time. Maybe the puzzle of fast radio burst will be solved before SK will start to operate. At least I hope very much for it. And finally, I want to say that there are lots of papers, lots of sources. lots of new results, but still lots of puzzles. If you are interested in the topic, I strongly recommend to start with this review published in Nature in November. It's relatively brief, as it was published in Nature, but it covers all main topics, and it's very recent, very updated. And I'll stop here. Thank you very much.